So in the video today we will work again on the p-value concepts, and we will have to answer several questions. I will prepare one video for each questions just to have them separately. So the first question that we will work with is how p-values are distributed when the null hypothesis is correct. So let's assume that we study the differential gene expression, so expression of genes. And we have a sample from a population of healthy people. So we have, let's say, 5 healthy people. So we have the population of healthy, and we have taken 5 people from there, and we have 5 people from the sick population. Just a specific disease. So here we have gene 1, gene 2, and so on. And here we have the expression values of these 5 people. So expression value 1, 1, expression value 1, 2, expression value 1, 5. And here we have also expression value 1, 1, expression value 1, 2, up to expression value 1, 5. And let's suppose now that these genes here, their expression level is not affected by the fact that a person is healthy or sick. So for these genes, actually, the null hypothesis is correct. Remember that the null hypothesis states that the mean value of healthy people, for the expression level of the healthy people, is the same as the mean value of the sick people. Again, the mean values here refer to the populations. So it's like we have a normal distribution with some mean, m1, that this distribution gives values to the healthy people. And another distribution, the red one, with the same mean and the same distribution, in fact, the same variance, that gives values to the sick people. So these 5 values are coming from the red distribution, while these 5 values here are coming from the black distribution. But in fact, these two distributions in this case are the same. So the null hypothesis holds here. Okay, and let's now see what kind of p-values we would expect here. So according to the definition of p-value, is that if we construct a statistic from these values, and we said in previous lectures how to construct the t-statistic, given that the null hypothesis is true, the t-statistic is distributed like that. And if our observation here is some value t1, so we have used these 10 values, and the mean of these 10 values and the mean of these, the average of these 5 values and the average of these 5 values, and the variances of these 5 values and the variance of these 5 values to construct the t-statistic here. And we have calculated a value t1 for the t-statistic for the gene 1. Now this value is here. The p-value associated with this first gene is this area here if the alternative hypothesis is that healthy people have greater expression value than sick people. So with this alternative, this is the p-value. So this is the probability to find a value greater than t1 when the h0 is correct. Now, in this case here, the null hypothesis holds. The null hypothesis is correct because we said that we use genes that they come in fact from the same distribution in these two populations. So if the p-value for this gene, so the p1 is the p-value for the first gene, then it means that this probability here equals to p1. So which means that if the null is correct, the probability to find a number, to find an x for the t-statistic, a value of x for the t-statistic that is greater than t1 is in fact p1. However, if we find such a value, let's say t2, this t2 will have a smaller probability, will have a p2 which will be smaller than p1. So if we find such a statistic when the null is correct that is greater than t1, then this t2, which will be the second value of the t-statistic, will have a p-value p2 which will be smaller than p1 because the p2 is actually this quantity here. Therefore, we can say that the probability to find a t value or an x value here, which is greater than t1 when the null is correct, is p1. But by definition. But this means that the probability to find a smaller p-value than p1 when the null is correct will be p1. So I will write this down. So the probability to find a p-value which is smaller or equal to p1 when the null is correct is p1. Why? Because if we find a t-statistic value which is greater than t1, then this automatically means that this t-statistic value will be associated with smaller probability because it will be more extreme than t1, but the probability to find such a t is exactly p1, and therefore the probability to find a p-value which is smaller than p1 is exactly p1. So in general, the probability to find a p-value that is smaller or equal to some value x when the null hypothesis is correct is exactly x. But this one, this statement here, is exactly the definition of the uniform distribution. So this means here that the p-value follows a uniform distribution in 0, 1 when the null hypothesis is correct. Now we can see this also with code in R, doing some small simulation. Okay, let me open R. So here I construct a matrix from 100,000 values. All of them are coming from a normal distribution with mean 100 and variance and standard deviation 10. And these 100,000 values are distributed in 10,000 rows and 10 columns, forming a matrix. So since I have 10 columns here, I assume that 5 of them are healthy and the other 5 are coming from the class disease. So I have 5 healthy and 5 sick people. But again, notice that each value on the table is coming from the same distribution. Therefore, it's similar to what we said here, that the values of the healthy people and the values from the diseased people, from the sick people, are coming from the same distribution. Which means that the null hypothesis is actually correct here. Okay, let's go now to calculate p-values. So I wrote this small function to calculate the p-value of each row, and now we'll get these p-values. Okay, I think it's done, and the distribution of these p-values is here. And this distribution actually is the uniform distribution. So you can see with a small simulation here that indeed the p-values are distributed normally when the null hypothesis is correct. Okay, this is the first video, and then we'll go to the next questions.